Dear students, today we are discussing the paper Differential Equations of 5th semester BSc Mathematics under MG University. In the previous class, we already discussed the first three sections of Module 3, Power Series Solutions and Special Function. Today, we are discussing the last section, more on regular singular points. You are already familiar with the ordinary points, singular points, regular singular points, initial equation, Frobenius series solution, etc. Today, we are discussing what will be the solution of a second order differential equation by analyzing the roots of an initial equation. Initial equation is a quadratic equation here. In M, it has two solutions. So, we have the theorem. Suppose that x not equal to 0 is a regular singular point for the differential equation y dash plus p y dash plus qy equal to 0. So, here we are assuming the differential equations with the only regular singular point as 0. So that the power series for x into p of x and x square into q of x how the radius of convergence are greater than 0. Suppose that the initial equation m into m minus 1 plus m into p naught plus q naught has roots m1 and m2. The first case is with m2 less than or equal to m1. So that differential equation has at least one solution. Either m2 less than m1 or m2 equal to m1. Differential equation has one solution y1 equal to x raised to m1 sigma j equal to 0 to infinity aj xj on the interval minus r. Further, in the case m1 minus m2 is not 0, m1 and m2 are different, or the difference is a positive integer, then the differential equation has a second independent solution, say y2 equal to x raised to m2 sigma j equal to 0 to infinity bj x raised to j on the interval minus r. So, we have the example xy2 dash plus 2y dash plus xy equal to 0. To solve this differential equation, we have to write it in the standard form. Obviously, it has 0 as a regular singular point as per the theorem, but we have to check it. So, the standard form is y2 dash plus 2 by x into y dash plus y equal to 0. From this standard equation, p of x is equal to 2 by x and q equal to 1. Here x not equal to 0 is a singular point. From the definition of p and q, the division by 0 process occurs only by putting x not equal to 0. So, x not equal to 0 is only singular point. Further, x minus x not into p of x is x into 2 by x equal to 2. Analytic at x not equal to 0. It's a constant, so it is analytic. Again, x minus x not the whole square into q of x, that is x square into 1. Putting x equal to 0, it will become 0, so that analytic at x not equal to 0. So, x not equal to 0 is a regular singular point for the given differential equation as per the theorem. Then, for writing the initial equation, we have to calculate p naught. The equation of p naught, you already know that limit x tends to x naught, x minus x naught into p of x. Here it is limit x tends to 0, x into p of x, that is 2. So, the limit is 2, is a constant. Again, q naught equal to limit x tends to x naught, x minus x naught the whole square into q of x. Here it is limit x tends to 0, x square into 1, it becomes 0. Hence, the initial equation, the standard form of the initial equation, m into m minus 1 plus m into p naught plus q naught equal to 0. Here it is m into m minus 1 plus 2m plus 0 equal to 0. So, it is a quadratic equation in m. That is m square plus m equal to 0. Putting m out, m into m plus 1 equal to 0. So, that we have two roots, m1 equal to 0 and m2 equal to minus 1. For m1 equal to 0, we have the Frobenius series solution. The general form of the Frobenius series solution contains term x raised to m. Here the power m equal to 0, so that the series now become y equal to a0 plus a1x plus a2x square plus a3x plus a4x raised to 4 plus etc. Then you already know that y dash is a1 plus 2a2x plus 3a3x square plus 4a4x plus etc. and y2 dash is 2a2 plus 6a3x plus 12a4x square plus etc. Substituting these three series in the given differential equation, we have x into y2 dash 2a2 plus 6a3x plus 12a4x square plus etc. plus 2 into y dash a0 plus 2a2x plus 3a3x square plus 4a4x cube plus etc. plus x into y a0 plus a1x plus a2x square plus a3x cube plus a4x raised to 4 plus etc. equal to 0. For further solution, further steps of solution, we have to open the bracket by multiplying the series with the terms in the outside. So in the first term, all the terms raises the power of x by 1 because we are multiplying with the x. In the second term, we are multiplying series by constant, so there is no change in the power of x. Again, the third term, the power of x raised by 1 by multiplying through the series by 1. So, comparing the coefficients, first we have to compare the constant. Here the only constant, after opening the bracket, the only constant is 2a1. So, we have 2a1 equal to 0. 2 is a constant, so that a1 equal to 0. Again, compare the coefficients of x. It is 2a2 here. Here it is 4a2. Here it is a0. So, we have 2a2 plus 4a2 plus a0 equal to 0. This implies a2 equal to minus a0 by, here it is 2 plus 4, 6. So, a2 equal to minus a0 by 6. Further, the coefficient of x square, it is 6a3 plus 6a3 plus a1 equal to 0. That we have 12a3 plus a1 equal to 0. So, that 12a3 equal to minus a1. But a1 is already 0. So, it is trivially 0. Again, the coefficient of x cube, we have 12a4 plus 8a4 plus a2 equal to 0. Next step is 20a4 equal to minus a2. So, that a4 equal to minus a2 divided by 20 is equal to, but we know that a2 is already minus a0 by 6. So, minus into minus become plus, so that a0 by 120. So, substituting these values of a0, that is already non-zero, a1, a2, a3, a4, we have the solution for m1 equal to 0 written as y1 equal to a0 plus minus a0 x square by 3 factorial plus a0 x raised to 4 by 5 factorial plus etc. Further, for m2 equal to minus 1, we have the Frobenius series solution as, here the power is power m equal to minus 1, so that x raised to minus 1 into a0 plus a1x plus a2x square plus a3x cube plus etc. Opening the bracket, the first term is a0 by x, second term is a1, third term is a2x, and so on. So, taking the first derivative y dash equal to, the derivative of the first term is minus a0 by x square, second term is a2, third term is 2a3x, the fourth term is 3a4x square, and so on. Again, the derivative of y dash is y2 dash, the first term becomes 2a0 by x cube, second term becomes 0, third term becomes, the second term of the y dash becomes, derivative of the second term of the y dash becomes 0. Third term, the derivative of third term 2a3x becomes 2a3. Then next term is 6a4x and so on. Substituting these three series in the given differential equation, we have x into y2 dash 2a0 by x cube plus 2a3 plus 6a4x plus 12a5x square plus etc. plus 2 into y dash minus a0 by x square plus a2 plus 2a3x plus 3a4x square plus etc. and so on, plus x into y is x raised to minus 1 into the series a0 plus a1x plus a2x square plus etc. So, is equal to 0. By opening the brackets, the first series become, the first term of the first series become 2a0 by x square, second term is 2a3x, and so on. And here onwards, all the term raises the power of x by 1. Again, in the second term, multiplying the term, the series by 2, we have first term is minus 2a0 by x square plus second term is 2a2 plus, and so on. There is no change in the power of x, only changes in the coefficient. The third, opening the third bracket or the third term in the differential equation become x into x inverse become 1. So, the series remains still a0 plus a1x plus a2x plus etc. equal to 0. For comparing coefficients, we have the lowest power of x as 1 by x square, x raised to minus 2. So, we have the coefficient 2a0 here, here it is minus 2a0. So, it is automatically becomes 0. So, the next is constant, the only constant term is 2a2 here and here is a0. So, we have 2a2 plus a naught equal to 0 implies a2 equal to minus a naught by 2. 2 is 2 factorial. Again, coefficient of x. Here it is 2a3. Here it is 4a3. Here it is a1. So we have 2a3 plus 4a3 plus a1 equal to 0 implies a3 equal to minus a1 by 6 is 3 factorial. Further, coefficient of x square, we have 6a4 plus 6a4 plus a2 equal to 0. But that implies a4 equal to minus a2 divided by 12. My a2 is already minus a0 by 2 factorial, so it becomes a0 by 4 factorial. Further, coefficient of x cube, that is 12a5 plus 8a5 plus a3 equal to 0 implies, as in the similar way, we have a5 equal to a1 divided by 5 factorial. Substituting this a0, a1, a2, a3, a4, a5, etc. we have a solution for m2 equal to minus in terms of coefficients a0 and m. That is y2 equal to a0 by x plus a1 plus minus a0 by 2 factorial x plus minus a1 by 3 factorial x square plus a0 by 4 factorial x cube plus etc. We can further arrange this series. So we have the solution y equal to y1 plus y2. y1 can be written as a0 taking a0 outside a0 into 1 minus x square by 3 factorial plus x raised to 4 by 5 factorial plus etc. Plus from y2 taking a0 common, we have a0 into 1 by x minus x by 2 factorial plus x cube by 4 factorial plus etc. And taking a1, we have a1 into 1 minus x square by 3 factorial plus x to 4 by 5 factorial plus etc. So existing like 3 times. By combining first and last series, that is, the series is common for first and last term. So a0 plus a1 into 1 minus x square by 3 factorial plus x raised to 4 by 5 factorial plus etc. We can take an x outside from the series. So we have a0 plus a1 divided by x into x minus x cube by 3 factorial plus x raised to 5 by 5 factorial plus etc. This series is signed. Further, from this term, that's a0 into this series, taking an x outside in the denominator, we have 1 minus x square by 2 factorial plus x raised to 4 by 4 factorial plus etc. That's a0 by x into 1 minus this series, that is a0 by x into this series, cos x. So we have the solution as a0 plus a1 by x into a0 plus a1 by x into sin x plus a0 by x into cos x. That is the solution of the given differential equation. So discussing this section, we are concluding the third module. So we will see in the next class. Thank you.